Hi everyone. First of all, thank you very much for inviting me and giving me a great opportunity to interact with very bright Taiwanese students. So my name is Gunhee Kim, and I'm from Seoul, of South Korea. And today my topic is about memory networks. So I guess some of you may heard about memory network, and part of you may not know about memory network. So this is the outline of my presentation. So my lecture is a kind of tutorial for memory networks, and then I will shortly introduce our own research that uses memory networks for various applications. So actually, memory networks are studied by, mainly proposed by two different groups. So the first, as you can see, the first group of work was done by researchers in Facebook, and the second group of work was done by the researchers in Google. So actually they are proposed somewhat independently. So I'd like to introduce these two different approaches first, and then finally I will shortly introduce our own applications. First one is text summarization. Given a very long passage of text, our goal is to summarize it in a single sentence. Actually, text summarization is quite old problem, but it's still not solved. So it's still very difficult problem. And the second application is we use memory networks to solve two problems of unsupervised learning of GANs. I guess many of you already know about GANs, but almost all GANs suffer from two issues. But we resolve these two issues using memory GAN. So I will introduce that work as well. So, okay, let me begin my presentation. So first I will introduce the motivation of memory networks, why we need to care about it. So actually, I will first compare memory networks with CNNs and RNNs. I guess those two approaches are the main building blocks of recent deep neural networks. And first of all, this slide summarizes the convolutional neural networks. As you know, convolutional neural networks consist of a sequence of these three computation building blocks: convolution operation and nonlinear activation function and pooling. You repeat this process again and again, and then the final feature map can be regarded as a high-level feature for the input image. And then that feature is very good, so you can just use very simple classifier like softmax, but still you can get the best result, state-of-the-art result. It means that feature learning is so good. But the thing is that we'd like to think of what the CNN learns. Actually, what the CNN learns are a set of filters, right? A set of hierarchical filter sets. So even though you train your CNNs with millions of images, but what the CNN memorize are filters. So that's what the CNN memorize, but they do not directly memorize the image themselves. They only learn filters. And then the second, the most important building blocks of neural networks is recurrent neural network. As you know, it takes a sequence of inputs and then it keep update the hidden state, right? So as you know, this shows the unfold along the time view of recurrent neural network. So key idea is that if you apply RNN to do machine translation, you take a series of words in one language, and then you decode it into a sequence of words in another language. So in order to that, you sequentially input one word one by one, and then RNN update its hidden state again and again. And once you finish inputting the word sequence, then the final hidden state can be regarded as the embedding of input sequence, right? From here, then you can generate words one by one in another language. So in this model, one issue is that it mix computation and memory. So in this model, there's only single memory slot, so which is a hidden state. So actually, hidden states is a fixed dimensional vector. For example, you can set the dimension of a hidden state like 500. Then you only have 500 vector as memory. So suppose that your input sentence consists of 50 words, but still you have a single vector, right? But you probably know that it may not be sufficient to memorize very, very long input, right? So that's one issue. So it has only a single fixed implicit memory, which is a hidden state, and this model is a kind of a mixing of computation and memory. And then another issue is that much information is lost with a sequence of nonlinearity. So in the example of 50 words, so let's focus on the first word. First word is input, and you apply nonlinear activation to the hidden state. And then second word is input, and you apply nonlinear activation again. So from the point of view of the first word, it keeps getting nonlinear activation again and again and again. So it means that the information of the first word may be lost in long time scale by applying so many a sequence of nonlinearity. So that's another issue. And by this issue, many RNN suffer from gradient vanishing, and catastrophic forgetting problems. So it has a limitation to memorize a long sequence of word information. So that is very well-known problem. So the basic idea of memory network is to separate memory with memory from computation. So previous RNN models mix memorization and computations, but here our focus is we introduce a very big external global memory, and you put the information into the memory, and then later you can only access relevant information in the memory to generate the output. So it means that it reduces the burden of memorization to the model, right? So that's a key idea of memory network model. And I slightly changed the order of slides. So originally, this slide is page 19, but I first introduced this idea before introduce memory network model. So in the example of plain RNN, as we discussed, inputs are fed to RNN one by one in order. So in our machine translation task, you input first word and then second word and so on. But in the memory network, you don't need to do that. You first put all information in the memory. And then later, let the RNN decide which part read next. So, but on the other hand, RNN has only one chance to look at a certain input symbol. So, conceptually speaking, if there is a 5 words like that, there is only a single hidden state in RNN. So you first input the first word, and this hidden state is updated, and you input again, and hidden state updated again, and you input the third word, fourth word, the fifth word, and then the hidden state will keep updated. But on the other hand, in memory network, you input the whole sequence in a memory slot. And then later, neural network access the most relevant memory slot and then generate a single output. And based on this output and the memory again, and it changed the access of the memory slot and then generate the second word again and again. So in the memory network approach, you don't need to memorize. You don't need to memorize, or you don't need to represent all words in a single vector. So that's a key idea of neural network. So here is a summarization of a memory network over RNN models. The first one is memory networks can take more generic format. So in the RNN formation, every single input should have the same form, right? If the first one is word, then second input should be also word, and so on. But in the memory network, you can use different modality of information. For example, here's a memory slot. So you input the word information here, or you input the location information, or if you can even input the image information, and so on. So it means that the model can take multimodal input in a very trivial way. So that's one important memory network advantage. And the second thing is that memory networks allow out-of-order access to the input data. So yeah, as we discussed in RNN, you should first decide the order of input, right? And then you put the input one by one. So you have to fix the order of input, right? But in the memory network, you just put the input in memory slot, and then later let the model to decide which information to access to generate an output. So it means that you can access the input information in out of order. So that's another important advantage. And then the third one is memory networks are less distracted by unimportant input. So again, RNN takes the input one by one. So suppose that the length of input is 50, and some of them may not be so important, but RNN should consider every single input equally. So that's the issue. But in the memory network, suppose that you input the input information into the 50 slot. If there are some of them are not important, then you can just ignore it. You cannot just not access the unrelevant information. And the fourth advantage is it has long-term memorization ability. So it's very straightforward. So you explicitly memorize the input information in separate memory slot. So it's too trivial to for memory network have long-term memorization. So due to this effect, memory network does not suffer from does not suffer from vanishing or exploring gradient problems. So main cause of this problem is you apply the same same W, which is some model parameter. You apply the model parameter, the same model parameter again and again. So that causes the instability, such as vanishing and exploding gradient problem. But in memory network, there's no such operation. There's no such iterative multiplication of the same matrix. So these are the main advantages of memory network over RNN. So if you have any question, please feel free to interrupt me. So yeah, this is the end of very short introduction or high-level motivation of a memory network model. And from now, I will introduce memory networks, one of the first memory networks. So in this subsection, I will introduce these two papers. So this is the first memory network paper, which was published in iClear 2015. Shortly, right after this paper, they published another paper. So the same authors published the same upgrade version of memory network model. So in this lecture, I'd like to start from the second one because the second model has many good advantages over the first model. So I'd like to focus on the second paper. So this is a summary of the memory networks. So this is a neural network model with large external memory. And the key idea is you just write all input or relevant information to the memory, and then later let the model to decide which part should to be read. So you can only read only relative information. But the issue of the first paper is that they use hard addressing. Hard addressing means that you need to apply max of the inner product between the internal state and memory content. So it means that you use max operation, so it's not differentiable. So it means that it's not trainable end-to-end. So that's one critical issue of the very first model. So, and then here I summarize the disadvantages or problems of the very first memory network model, which was published in iClear 2015. So the first problem is that it requires explicit supervision of attention during training. So you have to have labeled the information to which memory slash should be accessed. So it's very tricky to get such kind of labels, such kind of supervision. And the second problem was it was only applicable to very simple tasks. And the final one was the critical issue. So it was based on hard addressing, so it's not end-to-end trainable. So that's the main reason why the title of the second paper was End-to-End Memory Networks. So simply speaking, the second paper was an improved model that can be trained end-to-end based on memory networks, which was published in iClear 2015. So from now, I'd like to explain this model in a very detail, because it's the basic, one of the most basic model for memory networks. So if you can completely understand this model, then it would not be difficult to understand other models. So I'd like to spend sufficient time to explain this. And if you have any question about my explanation, please feel free to interrupt me to ask a question. So yeah, this is the summary of Antrem memory network, and Antrem memory network is shortened by MEM end-to-end. And the first major improvement is memory accessing is changed to using soft attention. So as briefly talked about in previous slide, the first model uses hard addressing, but here it is changed to soft attention for memory access. By doing that, the model is trainable end-to-end. So you only need final output for training, and backpropagation is very easy. And another important update is multiple memory lookups. So yeah, I will talk about the detail in next slide. So major advantages of multiple hops is it allows the model to have more reasoning power. So I will explain that with an example later. So first of all, I'd like to introduce this model with this application. So the target task is question answering. So this is very simple question answering. So there are 4 input sentences, and now you get the question, and your goal is to answer this question. One constraint here is that the answer consists of only a single word. So human can easily answer this question, but neural network was not able, but now it can do. But the key thing is that the input is very long. I mean, this input should be memorized. So here there are only 4 short sentences, but it is also possible to have very long input sentences. And then in order to correctly answer this question, you have to memorize all input sentences, and then you have to select some of the relevant sentences to answer this question, and then you make an inference to find out the final answer. So it's not a simple task for a machine learning algorithm. So here the inputs are threefold. The first input is a set of sentences, which is denoted by xi. So this is x1, x2, x3, and x4. And there is a query sentence, which is a question, and what you need to predict is a single word answer A. And in order to correctly solve this problem, word and sentence orders matters. For example, in the first example, if you change the order of the third and fourth sentences, then question will be different, right? The answer will be different. The answer should be kitchen, right? If you change the order of third and fourth sentences, right? So it means that word or sentence order matters to correctly answer this question. So actually, this is a model of the MEM end-to-end. This is a schematic illustration of a MEM end-to-end model. So I will explain one by one. So the first one is, there is a question here, and the question is a sentence, right? Question is a sentence. So it is represented by bag of words vector. So question is represented by bag of words. And then you first perform query embedding. Query embedding means that you multiply a matrix B and to get the low-dimensional vector U for Q. So this B should be learned during training. And then you use the same idea, same embedding idea to the input. So here's a sentences xi. So every single sentence indicates this sentence one by one. And you put these sentences into memory. But the important thing is, important thing is that there are two different types of memories: input memory and output memory. So same sentences are embedded in two different ways. So the first one is called the input memory, and the second one is called the output memory. So I will introduce why these two types of memories are required in very soon. So anyway, so the input sentences are embedded in the same way as query embedding. So, but with different matrix A and C. So A and C also learned during training. So now you have two different type of embeddings of the input sentences. And then the natural question is why we represent input into two different memories, input memory and output memories. So the idea is that the input memory is used to compute attention on the memory. And then the second memory is required to get the memory output. So it means that you have a query, right? And then the next problem is that you have to decide which memory slot should be read, right? Which slot should be read. So it is represented by attention weight. So if this slot has a high attention weight, it means that in order to correctly solve this query, you need to focus on this memory slot. So the first task is you have to compute this attention weight. So attention weight for memory access, which memory slot should be accessed. So in order to compute attention weight, you need to compare this query and the memory slot content, right? So here's the memory slot content, and you compare query and memory slot and query and memory slot and query and memory slot. By doing that, you can decide which memory slot should be focused, right? So once you get this weighting, then the next task is to compute the memory reading output, right? So in order to memory reading output, you have to merge the content of the memory according to this attention weight. So that's the main reason why we have two different memory representation. The first memory representation is needed to compute the attention weight, and the second memory representation is required to get the memory output according to this attention weight. So yeah, this is very important thing and somewhat confusing things. So any question about this idea? Okay, so
how do you ensure that you
So actually, during training, we are going to learn A and C. So what we expect is that the memory will learn what is the best representation for attention computing and what is the best attention for output computing. So yeah, we separately learn these two representations during training. So yeah, first we represent a query and every single input sentences but in two different ways. And we have to learn A and C and B by the training data. So next step is we compute attention into memory. So it means that here's a query Q, and by embedding B, the query is represented by U, and then its key idea is that you perform dot product between U and the memory slot vector again and again. And then you apply softmax. So that's the key idea. So it means that you compute the conceptual similarity between U and every single memory slot, and then you apply softmax. Softmax is required to get weight, right? Because the summation of all of this value is going to be 1, right? And every value will be larger than 0. So actually, this equation, probably you may see this equation in attention papers. So this is called soft attention. So yeah, almost all soft attention algorithms use softmax on the similarity. And then once you PI indicates this vector, PI indicates this vector, and then the next step is to generate output. So simply speaking, it's a weighted summation according to PI. It means that if this memory slot has a high value, it means that the content of this memory slot is very relevant to the query. Then we get the final output vector with more focus on this memory slot. So the equation is very simple, right? The first one is normal soft attention, and second one is simple weighted summation of all memory slot contents. Yes?
Based on your models, you need to separate your sentence, and how did you define the input of the input layer dimensions, the weight, and the output?
So Q is back-over representation. So its dimension will be decided by the size of your vocabulary. And then you have to decide the dimension of embedding. So therefore, if you decide your embedding dimension is D, then the dimension is going to be, B is going to be so V is the size of a vocabulary, and D is decided by U. As a result, this representation is going to be N by D. So here N is the number of memory slots, right? It's also decided by yourself. So they are the hyperparameter. And the dimension of a PI is going to be N, R to the N, because this is a value for every single memory slot, and it will also have the same dimension with this. And the dimension of output is also going to be right. So dimension of output is going to be R to the D, because you make a summation over N, over all memory slots, right? So in this visualization, this is going to be D, and this is going to be N. So there will be an n-dimensional n number of slots, and each memory slot is represented by d-dimensional vector. So anyway, the model is pretty simple, right? So once you get the output, so this is the output of memory reading. So here's a query, and you compute which slot should be attended, and based on that, you get the output of the memory reading. And the next step is you simply multiply, make a summation between U and O. So this is the output of a memory reading, and this is the input. And then you apply fully connected layer and softmax classification. So you apply W and then apply softmax, and then you get the answer selection dimension. So answer selection output. So dimension of W is going to be size of V by D. So these two vectors are going to be R to the N, R to the D. Therefore, W should be R to the size of V by D. So this is the size of vocabulary. Size of vocabulary. It means that you perform classification over word vocabulary. And if some vocabulary has a high value, it means that that word is going to be answer to this question. So softmax over sum of Korean averaged memory output. So this is the averaged, weighted averaged memory output, and you make a summation between U and O, and then you apply fully connected layer W, and then finally you apply softmax, and then you get the answer output. So the model itself is very reasonable and straightforward, and every single equation is pretty easy, right? It's a linear multiplication with softmax and summation and so on. So the overall architecture is pretty simple. Any question about basics of Antrem model? Yes? Yeah. Input sentence? Yeah, so embedding of input sentence should be also learned during training. So xi is the input sentence, mi indicates the vector of every slot. So it's obtained by multiplied by a, and a should be learned during training. Word by word. So yeah, that's very important problem. I mean, there are many word embedding algorithms, but there are very few successful sentence embedding algorithm, right? Here, you just represent each sentence using bag over words vector. So bag over words vector. So if input sentence consists of 4 different words, then bag over words vector is going to have 4 non-zero value, right? And then make a normalization. So that's going to be a sentence representation. Yeah. And that's going to be xi.
So based on your models just have the 3 layers, input and weight and output. So in the beginning, we just input a sentence to go after the initial model. And after that, if we want to start to input more data after to training, how to upload our weight.
In this model, we assume static case. So we assume that input is given at the first stage. So you put every single input in the memory slot, and then you apply this algorithm.
Okay. So you think about the questions that should be very similar with the sentence or not? If
Yeah.
Yeah. Okay.
So the thing is that, so for example, in this example, the question contains the word apple, right?
Yeah.
So therefore, it is likely to focus on the sentence with words, sentence containing word apple, right?
Yeah.
So in this example, the second sentence and fourth sentence will get high similarity value, dot product value. Therefore, their rate will be more high, higher. So, yeah. So when you compute P weight, or attention weight, these two xi will have higher weight. So that's the basic idea of this model.
Yeah, but the question is, because based on your questions, you will pick up the sentence, the second and the fourth sentence.
Yeah.
But your answers just to relate it to the third base run.
Yeah.
Yeah. So how do your models to pick up the relations between these sentences?
So in this model, our expectation is that there are several learning parameters, and those learning parameters learn such information too. So as I said, this is one of the most basic model. So probably you may think of many different ideas, but they are not implemented yet in this very first model. So now we move to multi-hop reasoning. So multi-hop reasoning is that you apply this idea several times. So in the base model, you perform a multiple summation, and then you compute with multiply with W and prediction the answer. But multi-hop reasoning means that once you get this, you apply memory network inference again by using this output as an input to the second hop model. So it means that in previous model, when you compute this value, and this value is input to the considered as a query, and then you apply this process again and get the output here, and then you consider it again as a query, and you make a inference, and then you get this process to find out the answer. So multi-hop means that you access memory multiple times. So that's the basic idea of multi-hop reasoning. So in this original model, each layer has its own parameters, right? So here is xi, and here mi is computed by a1 and x1, and this output, what is the notation of this? So suppose that this is ni, then it's multiplied by xi. Now, if you perform 3-hop reasoning, then probably you may need to have 3 sets of C and A, right? So in this, every single A and C may be different. And layer input, the layer input of the next hop is going to be UK plus OK. OK means the output of kth hop and input of the kth hop. And the next U is computed by summation of this one and this one, right? But in practice, we use weight sharing. By doing that, we can reduce the number of parameters to be learned. So they propose two different approaches for weight sharing. The first one is adjacent. Output embedding for one layer is the input embedding for the second. Embedding for the one above. So it means that you make A2 is equal to C1, and C2 is equals to A3, and C3 is equals to W, and A1 is equals to B. So that's one way of weight sharing they proposed. So if you use separate A and C, then it means that the number of parameters you have to learn is very large. It means that you need to get many training data, or you may be at risk of overfitting. So they propose weight sharing, and they propose two different approaches for weight sharings. The first one is adjacent. Adjacent means that you let A1 is equals to B1, C1 equals to A2, C2 equals to A3, and so on. So AK plus 1 is equals to CK, and WT, W transpose, is equals to the final C. The final C is equals to W, and B is equals to A1. So that's the first approach for weight sharing. And the second weight sharing approach is weight layer wise. So input output embeddings are the same across all layers. So A1 is equals to A2, A2 equals to A3. So all of them are the same. And C are the same as well. Instead, when you compute the input of next hop, you introduce another matrix to learn, which is denoted by H. So that's another approach for weight sharing they proposed. So they compared the performance of these two different approaches in experiments. And here I summarize some model details. So probably you may not need to completely understand this part for memory networks. So they are kind of some heuristics to improve the performance. So the first model detail is about sentence representation. As I said, they first use the bag-over-words representation, so which is denoted by this. A is a matrix to learn, and Xij indicates jth word in ith sentence. So it means that every single sentence consists of many different words, but each word is considered equally. So that's the idea of bag-over words. And position embedding coding means that they realize that usually the first and last words are more important than the word in the middle, if in a sentence, in general, right? So in bag-over words representation, they use the same weight for all words, but position embedding use a weight like this. So it means that you represent a sentence, you give more higher weight on the first and the last word. So that's based on assumption that usually in a sentence, the first or end words are more important than words in the middle. So they use a little bit complicated equation, but its basic idea is that they use a kind of weighting on the word.
Based on the position encoding, it just focus on the first and the last word.
Yeah.
Duration, not the whole sentence.
When you represent sentence, you give a slightly higher weight on the first and last words, and less weight on the words in the middle. So this is a visualization of this. So roughly speaking, it looks like this. And temporal encoding means that so in previous model, every single memory slot is considered independently. So if you change the order of the input sentence, but still there is no way to differentiate it between them. So in order to fix it, they use very, very simple idea. So they simply add a matrix to be learned to encode the order of information. So it means that it's kind of a lazy approach. So they do not try to come up with a good idea to model temporal encoding. They just add a parameter and let the model to learn it. So they don't care about it, and they just add the ability to learn such temporal information. And then there are other minor tricks. The first one is random noise. It means that you randomly add 10% of an empty memory slot. So suppose that if your input sentence is, number of input sentences is 10, then you randomly add 1 empty memory slot. And linear start means that you initialize the parameter of your model using linear model. Linear model means that except the last softmax to decide word prediction, you ignore all softmax and all nonlinear activation function. And then you only use a linear part, and then you first learn your model using such linear model. And then the learned model parameter is used as initialization of your real model. So that's the basic idea of linear start. And then now I will explain the experimental result. So there are, they use baby data set. So baby data set looks like this. And there are 20 tasks. So in the next slide, they summarize 20 QA data tasks. So for example, 3 supporting facts, argument relation, yes, no question, counting list, and so on. Simple negotiation, and so on. So yeah, all answers should be a single word, but they just classify the task into 20 different ones according to what the question asks. And you should answer question after reading short story. And one important property of this data set is that there are only 177 unique words. So there are only very few words only. And they only use simple language. A is B, and so on. And they train their model using 2 different sizes of training data, 1,000 and 10,000. And they also compare with many different variants. And based on that, they get this quantitative result. So it's too big to understand. So in next slide, I summarize the key result. The first one is that the proposed MEM end-to-end works the best compared to RNN-based model, I mean LSTM, and memory network. I mean the very first memory network model. So MEM end-to-end was the better than LSTM and memory network. And position encoding improves over bag-of-words representation, and linear start helps avoid the local minima. Random noise improves the performance. Joint training helps. Joint training means that they learn a single model considering all tasks. So they also learn a model separately for each task. So they compare them, but they realize that joint training helps across different tasks. And more hops give improved performance. So, but the thing is, they only test up to 3 hops. So they did not test more, for example, 10 different hops and so on. So the next slide I summarized. This example shows why multi-hop reasoning is important. So let's first take a look at the first example. And here's our input, and this is a question, and answer is this. And support means that the fourth sentence is critical to answer this question. So in this example, in the first hop, the memory network focus on the third and fourth sentence. But in next hop, they correctly pointing out, give attention on the support sentence. Support sentence means the critical sentence or the most important sentence to answer this question. So this visualize PI. So this visualize, this. And then the second example is interesting because there are 3 different support sentences. It means that in order to answer this question correctly, you have to focus on all 3 sentences. Even you fail to focus on one of them, you cannot answer correctly. So interestingly, in the first hop, the model focus on the 5th sentence, and next they focus on the first sentence and then 3rd sentence. By doing that, they can answer the question correctly. If you do not use multi-hop reasoning, then probably the model only focus on this. Then probably the model may not be correct to answer this question, because in order to answer correctly, you have to use all 3 sentences.
So what is the difference between the hop 2 and hop 3? Just the 2 multi-layers, or another one is 3 multi-layers?
It means that in this particular example, there is a P, and there is another P, and there is another P. So this visualize P1, P2, P3. Yeah. Okay, so any question about the first model? Actually, this model is the most basic, so yeah, that's the main reason I spent enough time to introduce this paper. Yep.
Can a model answer questions that information that cannot be inferred from the input?
Yep.
Does it support that kind of? Can it answer that kind of question? I don't know. Is it through a random answer?
Yeah, actually, I think in that case, probably it will generate a kind of random answer. The basic philosophy of memory network is that you input everything relevant information. Then let the model to decide only relevant information selectively. So yeah, it's desired to put all relevant information in the memory. Yes?
What's the size of the largest memory network that has been used so far that you are aware of?
Actually, these days, there are also some research using large scale memory. But in current settings, there is a trade-off. If we use very large memory network, then the weight P is going to be also large. So in that case, it's not easy to correctly learn PI. And the second issue is that you perform weighted sum, right, to get the final output, right? But if your memory slot is too many, even though your model correctly focus on important memory slot, but if you perform summation of a whole memory slot, then it will be distracted by other non-relevant information. Even though every non-relevant memory slot has very, very low attention weight, but still, if you make a summation of all of them, then the correct information may be distracted. So there is a trade-off between small and large memory network, but still there are some papers that try to use very, very large or scalable memory network algorithm. So I can tell you if you ask personally. I mean, I can tell you the paper, some relevant paper.
I have a question. In our case, the sentence is almost defined because it's the verb. It's almost the same.
Yeah.
Want to travel to Toronto. And did you ever try to use the new sentence?
Yeah.
Because it's in our social media, our sentence would not to be right to this format.
Yeah.
So did you ever to try to input the new sentence that answer a question and the model to be successful?
So actually, we published a paper in CVPR 2017. So in the paper, we apply memory network model to Instagram data set. So the task was to automatically generate reply for the post, or if you take a picture, then its task is to generate post content and hashtag. So we apply memory network to that application, but yeah, the output is a little bit noisy, but it's still better than RNN-based model. So yeah, there are many open directions to use memory network. And I personally believe memory network is pretty good model, pretty good neural network paradigm. So personally, I apply memory network to video summarization and text summarization and post generation and so on. So yeah, that's the main reason why I chose this topic to introduce you in this tutorial. So I hope many of you also learn and use memory networks in your own problems. Yeah.
How do you choose the number of hops?
Yeah, there's a hyperparameter. So in practice, you have to cross-validation. Yeah, you have to do cross-validation. So yeah, you can guess how many hops are required to solve problems. So in this example, one rough guideline, maybe the number of hops may be similar to number of supports. for QA task. But yeah, that's a hyperparameter. Okay, I will move to the second paper. And the second paper, I will quickly talk about the second paper because it has upgrade memory network model, but if you correctly understand the first paper, it's not difficult to understand this model. So the second model is key value memory networks. So actually, this is a memory network. So you can use the idea of other fields of computer science to this application. For example, this is one example. In database, key value database or hash table is very commonly used technique. So you can use that idea here too. So, and personally, in Korea, I do project with SK Hynix and Samsung Electronics because they are very interested in memory network model because it names as memory. So probably they may be interested in this model. And another, their goal is to, recently people use GPU for neural network computation, but their ambitious goal is to replace GPU with DRAM. It means that, as you know, neural networks computations requires very simple operation, right? Roughly speaking, they only perform matrix multiplication, right? So by adding very small computation model to RAM, but it can perform neural network computation, then it will be much faster than GPU. So that's another reason why they are very interested in memory network model. So if memory network model turned out to be the best approach, best paradigm for neural network, then many people will use memory networks, then they will have more room to sell their hardware in neural network society. So yeah. So this basically, yeah, as I said, I will introduce two different approaches of memory networks. And the first approach is mainly done by Facebook researchers, and the second approach was done by Google DeepMind. And in terms of task, they mainly focus on QA tasks or summarization. And in the second approach, they mainly focus on general algorithm, like sorting or graph search and so on. So they use memory network as a specialized model for QA question. Because in order to correctly answer QA, you need to have some kind of a database, some kind of representation of your knowledge. So therefore, they developed memory network model. But in the second approach, the first paper was neural Turing machine. So as the name says, they try to design a new computer architecture, computational architecture. And they try to apply their algorithm to very, very general algorithmic problems. So anyway, in the second paper, they focus on the task of QA. I mean, this is a kind of traditional QA approach. So traditionally, they first construct knowledge base, right? Knowledge base. And normal knowledge base consists of like this. So there are a list of triples, and triples consist of subject, relation, and object. And based on knowledge base, you can answer this kind of questions. So there's a kind of traditional QA system, and in the QA system, they has some kind of a very well collected knowledge bases. But suppose that you perform QA task on knowledge base and compare it with QA system using raw text. So there are pros and cons. So if you use knowledge-based approach, then QA is easy and fast because our knowledge is already constructed in a structured form. But the second issue is that making such kind of knowledge bases require many hand labeling, manual labeling, so it's very difficult. And another issue is that there is no flexibility. So all information consists of 3 tuples. But suppose that you design your QA system using raw text, such as Wikipedia. So raw text always contain more information and can be scalable. But the issue is that retrieving answer from text is harder. So the issue is harder. So yeah, there is a trade-off between QA system on knowledge base and raw text. And the goal of this paper is that they try to develop a neural network algorithm that can reduce the performance gap between using a knowledge base and raw text. So for this purpose, they introduce Wiki Movie benchmark. So they collect a new data set, and they also propose a new memory network model. So this memory network model can perform QA tasks not only on knowledge base, but also in raw text. So they can be applicable to many database types. So that's the goal. And their main goal is that they try to design a new model that can work on not only knowledge base and raw text. And as you can easily expect, the performance on knowledge base will be higher, but their goal is to reduce the performance gap. So that's the main goal of this work. And they also develop a new data set to compare them. So this is an overview of key value memory network. It can leverage both knowledge bases and raw text data for QA. And it's an extension of a memory network. And it generalized the way context means the input sentences. Context is stored in the memory. So the thing is that they construct memory in this form, key value memory network. So yeah, as you know, as I already said, in database, key value DB is common practice, and it is also called the hash table. So they design their memory structure in this way. So this is overall architecture. So I will explain one by one. So their main focus is how to structure memory. So in previous paper, they embed every single sentence, and then they put them in each memory slot, and they design 2 different memory representation, input memory and output memory. But here, they organize memory slots in the form of a pair of vectors, key and value, key and value. So I'd like to remind key value, what is key and what is value. So here's a DB, and you input a query, And the goal of DB system is to generate answer. So this is what we expect for DB system. So in order to do that, given a query, you have to focus, you have to find out which slot, which DB should be focused. And then once you find out the DB slot, then you retrieve the content of this memory slot, right? So that's the basic approach, basic operation of a DB system, right? So in this setting, you have to first find out which memory, which DB slot you have to focus on for a given query, and then you retrieve the content of that memory slot. And that's going to be a basic operation of DB. So key is used to design, key is used to find out which memory slot should be retrieved. So key is used for that purpose, and value means the value we need to retrieve for the output. So as you can see, key match memory to the query, and value match memory to the response. So that's the basic operation of DB. So yeah, actually we already discussed. Suppose that if your query is defined by d-dimensional vector, and here's a DB, and every slot has key and value, and actually key is a vector that has the same dimension of query. If query is a d-dimensional vector, then key should be also d-dimensional vector, and value is the value that should be returned for the output. So in this particular example, keys and values can be words, sentences, and vectors, and so on. So any question about the construction of a key value memory network? So as a starting point, you have to construct memory. So our assumption is that we already has a set of key and values, pairs. We already have a set of key and value pairs, and then we assume that we already have memory. And we are going to discuss how to construct memory in detail later. But here, in order to explain the model, let's assume that memory is already constructed, key and value, and so on. So these are the key, and these are the values. So there is a knowledge base, and knowledge base consists of m number of key value pairs, and key is going to here, and value is going to here, and the second key is here, and second value is here. So you construct a key value matrix, a key value memory. And the first task is key hashing. So suppose that there is a question X, and then we first pre-select a small subset of memory. So there are m number of memory. So you first pre-select hn number of memory slots. So in order to do that, you can use any hashing method. So for example, you can use inverted index, or you can use locality sensitive hashing. So yeah, any hashing algorithms you can use. So inverted index means that given a query, then you simply return memory slots that contain the word in the query. So inverted index means that you simply compare word by, you simply compute occurrence of word, and then if this memory slot contain the word in the query, then they are selected. So suppose that you first select the HN number of memory slots. And then the second step is key addressing. Key addressing means to compute this. So that is a PI, which is a attention weight in previous model. So here we compute PI in this way. So basic idea is very, very similar. So this is a query question, and QX over X means feature map. So yeah, in previous example we use BQ, but suppose in this paper they use more general representation. And then the key value, each of a key is also represented as a feature map. And then you multiply matrix A, it means that you obtain low dimensional embedding for question and key, and then you perform dot product and apply softmax. So roughly speaking, they use more general notation, but the key idea is exactly the same, right? In previous paper, they use U transpose MI and softmax. So U transpose MI means dot product is the same. U is identical to this, MI is identical to this. And then you apply softmax. So yeah, as I said, this representation looks more formal, but the key idea is exactly the same. So key addressing means to compute attention weight, PI. And then value reading, take the weighted average of the memory values. O is obtained by PHI is attention weight, and this is a representation of the key values. This is yeah, I need to check. I think this should be value, not a key. So, but they just perform weighted summation. So again, this part is also the same with the previous model, but they simply use better or more formal notation. As a result, they get the O. And they also use multiple hops. That's also the same with the previous model. So roughly speaking, this is a slightly extended version of a previous model, right? Every backbone element is exactly the same. They only their only proposal is to use key value memory structure, but the other part is almost identical. So here I will represent how to perform kth hop, multiple hops. So in the kth hop, query representation is represented like that. So yeah, this should be k minus 1. So the idea is that you add query vector and memory output and multiply by matrix. This is a matrix to learn. And then first query is computed like that. A multiplied by feature map over X. A multiplied by feature map over X. And then key addressing means computing PI, attention weight computation. So you can simply compute with this and this. But in previous slide, I used this notation, but QI is identical with this. So this is a simple generalization. And response is obtained by this. So this YI is a candidate, all possible candidate words, and then get the feature map, and multiply by matrix B to be learned, and then you perform dot product, and then apply softmax, and then find the word that has the highest probability. So again, this part is also the same. So with the previous model. So yeah, simply speaking, notation looks a little bit more difficult and more general, but the key idea is almost identical. So, but if you read the other papers, the key idea will be more or less similar. So that's the main reason why I focus on the first paper. Once you correctly understand the first paper, the understanding the other papers may not be difficult, because yeah, publishing paper means proving a single idea, single complete idea. So they do not try to completely overturn the model. So they simply add one solid model update. So once you understand the page backbone, then it will be not difficult to learn a new model. So now I will shortly discuss how to construct key value memory. So when I introduce memory model, I assume that the key value memory structure is already fixed. So one motivation of this model is to apply this model not only on general knowledge base, but also on raw text. So if you have knowledge base already, then you define key and value like that. So knowledge base consists of three tuples, subject, relation, object. So you can generate key value in two different ways. So you can use subject and relation as a key and value as a object, or you can use subject as a key and value as a relations, value as a object and relation. So there are two different. So it's very naive. And then if you use raw text, then you can generate key and value like that. So in the sentence level, you use key. If you use sentence as a key and the same sentence for a value, then it's completely identical to previous model, right? So they also propose other idea to construct key value pairs. So they use a window of keywords as a key and the center words as a value. So for example, in Wikipedia document, they use 5 sequence. For example, if you set W to 5, then they select 5 sequence of words as key and the center word as a value. So there are many variants. Or you can use a word window as a key and then title as a value. So roughly speaking, value should be directly relevant to the output of the memory network. That means value should be directly relevant to the answer. So it's totally up to you how to design your key and value pairs. So another thing is as I said, they propose a new benchmark, new data set, so which is called Wiki Movies. So you can download this data set from Facebook research page, and it consists of raw Wikipedia documents about a movie. So for example, this is a Blade Runner document, and there are 3 knowledge sources. The first one is classical graph-based knowledge base. So they construct knowledge base like conventional knowledge base, and they also generate similar knowledge base using automation method. The first one is human annotated, and the second one is machine annotated. And they also propose Q and answer pairs. So the thing is that their goal is to develop an algorithm that can reduce the performance gap between using knowledge base or raw text. So that's the main reason why they make this data set. So they collect many different sources and they generate QA pairs that can be solved by these different sources. And then they compare the performance. So in next slide, this is a setup of an experiment, and here's the result. So the thing is that their key value memory networks works better than previous approach. At the same time, their original goal was the performance gap should be reduced between them, but it looks like they failed to achieve this goal because performance gap is non-trivial. But again, what they argue is that their algorithm is much better than previous end-to-end memory network model. So these two are the previous approaches. So you can see the details of experiments in the paper, but their key message is here. And okay, so now in next, we are going to take a rest a little bit, and then in next session I will focus on this part, and in the third session I will discuss about the third part. And if you have any question about the first group of models, then please ask me at the beginning of the next session. Okay. Thank you for your attention.